Hi everyone. Today we welcome Meng Cheng from Yale University. He's going to talk about mixed state topological order in 2 plus 1 dimensions. So if you're ready, you can take it away.
Okay, thanks. It's a great pleasure to be here to talk about mixed state topological order. This talk will be mainly based on the work shown here. So done in collaboration with Tyler Ellison, who was a postdoc at Yale back then, and now he's a faculty member at Purdue University. All right, here's our outline of the talk. So I guess I'll start with a very brief sort of motivation. So why this problem? What problem I'm going to trying to solve, and then why it's interesting. And since I'm not entirely sure, the background of the audience, I'll have a pretty lengthy sort of review of introduction to ground state topological order, mainly from the perspective of higher form symmetry, which can be generalized to mixed state later. And then I'll talk about just some basic notions of basic notions in open quantum systems, density metrics, quantum channels, and also strong weak symmetries. Okay. And then I'll discuss physics of decohered topological states from a couple examples. Okay. And then, if time permits, I'll discuss a kind of general conjecture for general classification. Okay. All right. So the motivation, the general sort of problem is to understand phases of matter. So this could be phases of matter in condensed matter systems or phases of quantum field theories. Okay. And in particular, I'm interested in the so-called topological phase of matter. And the canonical examples of topological phase of matter arise as basically ground states of a gapped Hamiltonian. Okay. And the system is usually assumed to be isolated. So we can talk about ground states or a pure state of the system. and this is in 2 plus 1D. So it's well known that these topological order states support anion excitations, which have very interesting properties and even have some applications, potential applications in quantum information processing. Okay, but there's an important underlying assumption that the system is well isolated from the environment, so we can talk about ground state. All right. So of course, in reality, that's never the case. You always have all kinds of noise or disorder, or dissipation, or even just finite temperature. Right. Therefore, it's important to understand what happens to our understanding of topological order in the presence of these sort of realistic imperfections. Okay, so now let me give a little more precise description of what I mean by ground state topological order or ground state topological phases. Right. So here we are thinking about, again, ground states of gapped Hamiltonians with local interactions. Okay. This may be on a lattice model or maybe in a continuum, but I guess the key assumptions are local Hamiltonians and also there's an energy gap. So the consequence of an energy gap is that all the correlation functions of local operators decay exponentially, okay, as a function of the distance. So it's short-range correlated. So we are looking at the kind of the huge space of short-range correlated ground states of gap Hamiltonians and try to give it some structure. Okay? Of course, to give it some structure, we need to have a natural way is to define some sort of equivalence relations. We'll say that this one state is equivalent to another state. And the purpose of introducing equivalence relation is to kind of bring out certain universal properties that are invariant under this equivalence relation. So the equivalence relation that has proven to be extremely useful is the following one. So two states, psi 1 and psi 2, imagine these are 2 points in this big space of gap Hamiltonian ground states. If they are equivalent if and only if there exists a quasi-local circuit that connects one to another. Okay, so here by quasi-local circuit, I basically just mean a finite time evolution under some Hamiltonian. Okay, this of course doesn't have to be the Hamiltonian that we start with. It could just be some other Hamiltonian, but has to be local, and evolution takes finite amount of time. So if you can evolve one state to another under certain Hamiltonian, then we say these states are equivalent. Okay, so this evolution will modify local properties. For example, you check expectation value of some operators, it will change. Even like the details of correlation functions will change, but there are universal properties that remain invariant, and this notion of topological order basically captures these universal properties. Okay, so under this equivalence relation, this space is divided into different connected components. Right, these are the kind of illustrated by the different colors on this plot, and between them you have to cross a phase transition. You have to cross some point where the system develops some singularity. Okay, and this is often very common to represent this quasi-local Hamiltonian evolution in terms of a circuit, like a quantum circuit, okay, of finite depths. All right, and please feel free to interrupt me with any questions.
So actually, I can just ask anything
Sure,
to be
please.
more specific. For example, we are just talking about equivalence relations of the ground state or non-trivial phases. But what kind of specific phases this can be? For example, Z2 invariant topological any phase or something?
So yeah, so of course, to actually give a classification, you probably have to put in some more some conditions. But let's say there's no global symmetry, right? Then you have all kinds of topological phases, such as a Z2 topological phase, or the one that's described by some Chern-Simons theory, quantum Hall states, etc. Okay, so I'll get to example very quickly.
Okay, thank you.
Sure. Okay, so now, so this is from a perspective of kind of a Hamiltonian, and while a lot of the progress, a lot of understanding of this problem comes from quantum field theory. Okay, so let me briefly talk about the kind of field theory thinking about this problem. So we start from some Hamiltonian, gap Hamiltonian. Okay, and let's you can if you like to think in terms of field theory, just think about some UV weakly coupled field theory, some Lagrangian. And there's and we assume that in the deep infrared limit, meaning that we focus on ground states, then according to our assumption, there's a gap. Okay, then if the field theory start with is relativistic field theory, has Lorentz invariance, then the deep IR limit should be described by a topological field theory. Okay, so of course in field theory this is easy to understand, but if you start from a non-relativistic system or lattice model, this is far from obvious. This is a very non-trivial statement and has been sort of established in 1+1D and very widely believed to be true in 2+1D. And this fails in higher dimensions. So I'll limit myself to just 2+1D, where 1+1D is somewhat too simple, and 2+1D is where you have a rich family of interesting theories. Okay. All right. Okay, so let's say a 2+1D or 3D topological quantum field theory. This is a theory that only has topological line observables. And we kind of made the assumption that there's no non-trivial local operators. Mathematically, this is allowed, but following the kind of standard practice, at least in the condensed matter sort of literature, we assume there's no local operator except identity. Okay, so they have these topological line operators, and these line operators generate basically one-form symmetries, whose charged objects are again lines in 2+1. Okay. All right, so now let me give a concrete example. So I'll give this example in two versions. One is a field theory description of this example, and then I'll talk about the lattice one. So the example is a Chern-Simons theory. This is probably the most well-known, well-studied topological field theory. And it's very useful as effective field theory for fractional quantum Hall effect, toric model, or spin liquid, etc. Okay. So let's consider the following transaminase theory. So the gauge group is 2U1, U1 cross U1. Okay, and I'll call the 2U1 gauge fields as A and B, little n, a little b. So we write down this transaminase term with a coefficient 1 over pi times A wedge dB. Okay, so that's a transaminase term, and it's easy to check that this is a really good topological field theory. No. Okay. Okay. So what are the observables? While the observables, the gauge invariant physical observables are Wilson lines, you take the gauge fields and integrate the gauge fields along some closed loop, and then put in exponential, that's a Wilson loop. So here gamma stands for some closed loop. Okay. So there are two Wilson loops you can write down. One of them is for A and the other one's for B. So I'll call them WE for A and WM for B. Okay. It's just convention. And WE generates a one-form symmetry. You can check that it basically shifts B by by a connection lambda. Okay, the connection lambda is something that satisfies d lambda one form, closed one form, d lambda equals 0, and has proper periods when you integrate along some closed cycle. Okay, and we have these two operators, and it turns out that they generate Z2 cross Z2 one form symmetry. Okay, so this is the field theory version of this. So let me say one more thing about the one form symmetry that will be very important later. So we have these Wilson lines. We can also multiply them to get a third one. And turns out that these one form symmetry, just as any global symmetries, they have total anomaly. Okay, and in 2+1 for these line operators, the one form symmetry anomaly is basically equivalent to certain non-trivial exchange and braiding statistics between the lines. Okay. So for example, if you have M line wrapped around E line, which measures the one form charge of the E line under the one M line, you get a minus sign. This is just the usual statement that, well, when you link the two lines, you get a minus sign. Okay. Or if you have two psi line sort of exchanged, you get a minus sign. So that just means the sign is a fermion. Okay, so all of these exchange and braiding statistics we can phrase it as an anomaly of one-form symmetry, and it has all the consequence of anomaly, such as forbidding a trivial theory in the infrared. Okay, now here it's a topological theory, non-trivial topological theory. Okay, so what I just presented is kind of a really pure, pristine topological quantum field theory. So now let me make it a little more, let's say not interesting, but make it a little more close to what happens in an actual gap Hamiltonian. So for example, we can couple it to a matter, right? So far there was no matter. We can couple it to a scalar, and the scalar phi is coupled to A. We just couple it to A, has a mass and has some potential, etc. Okay. So now the theory is not topological. It has D here is a covariant derivative coupled of phi coupled to A. So it has some kinetic energy, has some potential energy. And we can assume that psi is massive. This parameter m squared is positive. So phi has a mass. And then below that mass, in the infrared limit, you still find the same TQFT. But now there's actually a finite energy gap. And above the gap, you'll find quasi-particle excitations, basically described by this field phi. Okay, so you now have some dynamics. It's not just a pure TQFT, it has some dynamics. Okay? So you can check that this one-form symmetry shifting B still remains because B only showed up in the transaminase term. Shifting B doesn't change anything else. So WE, which shifts B, is still a good one-form symmetry of this non-topological field theory. Okay, so that's still there. However, now if you shift A, which is generated by WM, because of the kinetic term, this is Lagrangian no longer invariant. So introducing this phi explicitly breaks the WM one-form symmetry. It's not there anymore. Right? That just says that you have some dynamic excitation, and these excitations break one of the one-form symmetries that preserve the other. However, because there's a gap, and once you go to the infrared, you still find the same TQFT, and that TQFT does have Z2 cross Z2 one-form symmetries. So this Wm, which is broken in the Hamiltonian, in the Lagrangian, reemerges as emergence symmetry in the infrared. Okay, and this will be this is more common when you actually think about a gap Hamiltonian, that you have emergent one-form symmetry. All right. So this is a story. This is kind of a simple example of a topological phase in the field theory. Okay, you have a kind of pristine TQFT description, and then it also shows up as an IR limit of a non-topological field theory. Okay, so now let me slightly switch gears and talk about a Hamiltonian on a lattice basically for the same phase. Okay, and the reason I'm going to do it on lattice, one reason is that thinking about decoherence and dissipation in field theory is somewhat not very easy. Okay, but on lattice everything is very clear. All right, and also the kind of realistic system that I have in mind are more like lattice Hamiltonians. All right, so this is the famous toric code model. I'm pretty sure that many of you probably have seen this before, so I'll be a little brief here. So the model has two-dimensional Hilbert space on the edges of the square lattice. These are qubits. Okay, and I'll use Pauli X and Pauli Z. So basically the red and the blue ones. The red is for X and blue is Z, okay, to write a Hamiltonian. And the Hamiltonian has two terms. Is a product of X on the four edges around one vertex, or the product of Z is around one plaquette. Okay. And this is sort of a Hamiltonian version of a deconfined Z2 gauge theory when the Gauss law is imposed energetically as a term in the Hamiltonian. So we can look at the ground states. So did I actually mess up color here? Probably, but because I use red to denote X, but okay. So we can try to write the wave function explicitly in the X basis. So the blue line means X equals -1, and no color means X equals +1. And Hamiltonian is basically, or the ground state is a superposition of all kinds of configurations where some links have blue colors because X is -1. And the first term in Hamiltonian means that all of these links have to form a closed loop because you have to have even number of -1s coming from one vertex. And then you have to superpose all such possible configurations that can be connected by locally flipping a small plaquette, and that's why you have the superposition. Okay. All right. Okay, so this is a Hamiltonian, right? You start from a bunch of qubits, and there's some local interactions. And this Hamiltonian, of course, has ground state and has all kinds of excited states. Because this Hamiltonian is exactly solvable, all the terms commute, we can describe the entire spectrum, not just the ground state. So spectrum can be thought of as in terms of the anion excitations. So basically, you can have either the vertex term or the plaquette term equal to -1. The ground state has all of them equal to +1. And if you have the vertex term, one vertex being -1, we say there's an M excitation. Okay. So to create M excitation, you have to apply a string of X along some path on the dual lattice. That will create two M excitations at the endpoints of the string. Okay. This time I have the color right. So the red one is just a bunch of X. Okay. So in the Z2 gauge theory language, you should think of M as the pi flux of the Z2 gauge theory. And similarly, you can have a string of Z's that create a pair of vertex violations. And these are the lattice version of the gauge charge. Okay. And you can have both. You can create a bound state of E and M, which is a dion, and this is actually a fermion. Okay, so you can also check that in this Hamiltonian, these operators which are, so the blue one is a product of Z's along some paths on the lattice. The red one is a product of X along some paths on dual lattice of any loop commutes with Hamiltonian. Okay, so these are conserved quantities. So here I call them one-form symmetry. Slightly abusing that term because they are actually not topological. They're just conserved. But I'm just going to call it one-form symmetry anyway. Okay, and here having these symmetries means that no anyons are dynamical. These anyons just sitting there forever. If you have an eigenstate with some violations of plaquette or vertex terms, they're just sitting there. They don't move. They're not dynamical. Okay, so that's what it means to have these kind of conserved loop operators. So in the infrared, they become topological, and these are one-form symmetries. Okay. So this is basically a lattice version of the Chern-Simons series that I wrote down earlier. Okay. So now I can also make it a little more interesting by adding dynamics to the anyons. So here I choose to add Z just to kind of parallel the notations I've set up earlier. So Z is essentially the same as putting in this complex scalar coupled to little a. Okay. And what it does is to make E anyons dynamical. You can see that it creates E anyons, pops them out of vacuum, and then moves them around. The M anyons remain non-dynamical. Okay. But again, if this term is small, if you don't perturb too much, then the ground state remains in the same phase. Okay. That means if you go to the deep infrared, you still see the same physics described by the same topological field theory. Okay. But if you now also want to include these sort of anyons, then you can have this non-topological field theory that describe also the dynamical E anyons. Okay. So this is the lattice version of the non-topological theory. Okay. All right.
Can I ask a question?
Sure. Yeah.
So we essentially associate the phase diagram of this toric model with H with the mass, like in this field theory, we have the mass, and if it's lower than 0, we broke the phase, we create a gap. So we associate these two parameters.
Sorry, two parameters. So I have a single parameter H. Well, G here is yeah. So I also introduced G because
I mean like by two parameters, I mean H in the lattice model and the mass in the field theory.
Right. Yes. Yeah.
Okay.
Right. Yeah. So no, as you increase H, that basically means that you decrease M squared until it becomes negative, and then it becomes 0 and negative, then you have phase transition.
I see.
Here, if you increase H above some threshold, you have phase transition to something else.
Okay.
Yeah. All right. So now let me look at the same model, but from the point of view of symmetries. Okay. So we have introduced these two symmetries, WE and WM. If you still remember the definitions, you can easily check that one of them still remains. The WE still remains, which is a product of Z still remains, right? Because I've introduced an additional term that's basically Z. So it still commutes with any product of Z. But the product of X, which I call WM, is broken by this term. Okay. So this is in parallel with the field theory that introducing these dynamical anyons explicitly break the symmetry that you begin with. One of the symmetries to begin with. However, again, in the infrared, if H is small enough that you don't cross the transition, then there's a dressed version of this WM, which I call WM with a tilde. It again reemerges as emergent one-form symmetry. Okay, so let me actually construct this tilde M operator, the dressed M WM operator. So I've kept saying that when H is small, this is in the same phase as H equals 0. Okay, and if you remember the definition of equivalence I gave earlier, so that means there is a quasi-local unitary generated by some evolution of local Hamiltonian that connects the ground state at H equals 0 to the ground state at finite H but small. Okay, before you cross a transition. So that's some unitary that relates the two states, and then I can just conjugate my Wm with a unitary. Okay. So as a result, Wm starts as a very nice operator, just product of a bunch of x on the lattice, something you can just write down. You conjugate this simple operator with some very complicated unitary transformation, and this operator is kind of blurred out, right? It's no longer that simple, but because it's Hamiltonian's quasi-local, it still kind of remains finitely kind of supported on the line. Okay? That means it has some support away from the line, but the support decays very quickly as you move away from that line. So it's no longer a simple, there's no longer a simple expression. So I drew it in this kind of very thick, blurred line. But that line still, the operator is still there. And this operator no longer commutes with Hamiltonian. Okay, it doesn't commute with Hamiltonian, but it keeps the ground state invariant. So the rest M operator generator is a symmetry of the Hamiltonian ground state, meaning that ground state is invariant on this operator. And WE is still there because WE still commutes with Hamiltonian. Okay. So here I assume that the ground state is on the infinite plane or S2. So they are emergent symmetries in the sense that they keep the ground states invariant. Okay. But they are no longer Hamiltonian, exact symmetry of Hamiltonian. So in that sense, they are all emergent, but because they come from applying a quasi-local unitary to these exact symmetries, the quasi-local unitary does not change, for example, commutation relations up to very small terms, which you can ignore. That means you have the same tooth anomaly for the dressed operators. Okay. So tooth anomalies are preserved under this kind of quasi-local unitaries because we just conjugate every operator by this U, and they will remain quasi-local and they will have the same anomalies. So this structure, the one-form symmetries and their anomaly are invariants in the face. Okay. So this is something that we can take to other situations where you no longer even have a notion of Hamiltonian, but you can still talk about emergent symmetries in the state of the state. Okay, so just see, I wanted to spend a lot of time on this discussion because this will be something that we can build on. Okay, but now with these examples in mind, now let me talk more generally about what we know about the ground state topological faces or topological order. So again, from a kind of a relativistic field theory point of view, the IR limit, we are basically trying to understand the IR limit, which is a topological field theory. Okay. In 2+1D, they are characterized by the category of line operators. Okay. So I'll just say that the mathematical structure of these line operators is a modular tensor category, which essentially determines a TKFT up to invertible series. So I'm going to ignore these invertible series for now. Okay. So there's a generalization of this story to higher dimensions where you can use more sophisticated topological operators to basically parameterize the TKFTs. But I'll stay within 2+1. Okay, so this is TKFT, but there's a very there are very good reasons to believe that the same applies to faces of gap local Hamiltonians on lattice, basically non-relativistic series. That you have the same kind of characterization of the faces. So I'm not going to say more about this. This, even though it's not proven, this is widely accepted and has, you can kind of verify in various examples. Okay. And there are recent works that try to put it on a more rigorous foundation. So another point that I like to kind of mention quickly is that so far, the starting point is you have a Hamiltonian and we look at the ground state. Okay? Hamiltonian has a gap and we look at the ground state. So the space is really the space of such gapped local Hamiltonians. And we're trying to do topology on this space, to give some structure on this space. But later on, when we need to kind of move away from this sort of Hamiltonian description, especially for mixed states where you don't have a Hamiltonian, it's more useful to think about the space of the states. Okay, so for topological classification purpose, heuristically, the space of short-range correlated states, short-range correlated ground states, is the same as the same for things like homotopy, the same as space of gapped local Hamiltonians. So you can just work with the space of short-range correlated states. You don't really need to start from a space of local Hamiltonians, okay? Even though that's probably what you actually want. And then topological order, so this is just heuristic description of very clearly that the idea that needs much more work to be more precise, but I just kind of want to motivate this description in terms more kind of state-based description, which will be more useful for the rest of talk. And we know the topological order is described by these emergent one-form symmetries, which keep the state invariant. Okay. So these are the kind of two takeaways from this discussion. Okay. All right. So this is end of my very long introduction. And maybe it's a good point to pause and see whether there are any questions.
Oh, maybe I have one question. Why don't we care about the surface operators in 2+1 DT fields?
Sorry,
What about the surface operators? Well, we only discussed
surface
line
operator.
operators.
Yeah. Okay, that's a very good question. Of course, we also care about surface operators. It's not that they are not important. So in 2+1, the surface operators, they basically, topological surface operators, they give you symmetries, zero-form symmetries of the TQFT. Right? If you have an invertible surface operator, that's an invertible symmetry, and you have also non-invertible symmetries generated by invertible surface operators. But this is a non-trivial fact that once you fix a line operator, you also determine all the surface operators, right? So this is a non-trivial fact. Maybe the more formal statement that you probably have seen somewhere is that all the surface operators are like condensation defects.
Okay. I see.
So
Okay.
the theory is fixed by the line operators, but the full structure, of course, you would also like to understand the surface operators, which you can kind of derive from the properties of line operators, and they give you a bigger structure, the fusion category.
I see.
Right. So, but for the purpose of classification, I only need to know the line operators.
I see. So specifying the data of the line operators, like the category, fixes also the surface operators. You don't have to worry about it.
You don't need to add that separately. It's basically contained in the line operators. The information is already there.
Okay. Thank you.
Okay. All right. That's a great question.
Hi.
Is there?
Yes, I have a question.
Sure. Yeah.
When you say the space of short-range correlated states, you mean that the difference of energy between the two states are finite or maybe small? Or what are you saying about this?
Okay.
So give you an easy example.
Right. So of course, the starting point is a gap Hamiltonian, meaning that I have a Hamiltonian and the ground state and first excited state has a finite gap. That gap remains finite in the thermodynamic limit if you take the system to very large. Okay. So above the gap, and if you go deep into the spectrum, right, into excited states, difference between energy becomes very small. You have lots of states within a very small energy window, right? Just because you have lots of entropy, you have to have many states. But below the gap, there's either a single or a finite number of states, and they are very close in energy. So that's a spectrum. Now, when I say short-range correlated states, I mean that in the ground state, if you go and measure the correlation of two local observables, the correlation decays exponentially as you move these two operators far away from each other. So there's very little correlation between local measurements on the states.
Okay.
So the states that's guaranteed by the gap, but no, you can also kind of impose that property separately. That there's not too much. There's not much correlations between what you do here and what you do over there.
Yeah. I guess this because it is not clear maybe in what space are we trying to do. Maybe in the left hand or your definition, you are referring to the space of states, right?
Yeah,
And
right.
the right hand or your definition is another space. I think so.
Yeah, so they're both space of some states, but the right hand is a space of really it's the correct statement that there's the more precise statement that the space of gapped ground states of local Hamiltonians. Okay, but so I just kind of replace it with the space of local Hamiltonians with a gap. Right.
Thanks.
Okay. All right. Okay, so let me say one more thing about this mathematical structure, the modular tensor category that underlines 2 plus 1 TQFT. So I just want to comment on the word modular. Okay, so mathematically, this is the structure that tells you how the lines, how they fuse and how they braid. So to make sense of, imagine you draw some picture of the lines where sometimes they can form networks or they can link in various ways. And this modular tensor category is a way to make sense of these pictures. They allow you to calculate the amplitude out of this picture, and this amplitude is topological. Okay. And the modularity is additional property that we condition and impose on these data. So to define it, we think about this simple picture of two loops linked with each other. Okay, so one of them is the line A, the other one is the line B. And the linking, if you compute the amplitude of this picture, you get a number. There's 1 over d, that's some normalization. So just basically the amplitude for a link of two loops. In space-time, you can think of as a B particle going around an A particle. Okay, so you can get a matrix out of this, just varying A and B over all the lines, you get a matrix. And the modular tensor category means this S matrix is invertible. Okay, and it has a clear physical meaning. The modularity means that the braiding between particles is non-degenerate. That you can detect the presence of particle A by perform some braiding experiment very far away from A. So you can kind of remotely detect the presence of some particle without touching it, okay, just using braiding. Okay, but mathematically, physically, if you want to describe ground state topological order, I should have said that this is in a bosonic system. Fermionic system is slightly different. So everything will be in bosonic system. I should have said it is in the very beginning. Mathematically, you can drop this condition. Basically, you allow the S matrix to be degenerate, and that's fine. There's no problem. And what you get is called a premodular category. Okay, it's just the same thing, but now we allow the S matrix to be degenerate. All right. And they will play an important role later. So here's one example of the premodular category. You just take the subgroup, Z2 subgroup generated by W psi, so that's a fermion line I define in Tori code, and just look at this Z2 subgroup itself. Okay. It's still a good modular tensor, it's a good premodular category because S matrix is having all ones in each entry of a 2x2 matrix and it's degenerate. Okay, that's a simple example. All right, so I think I'll need to move a little faster and now talk about mixed states. This is a very kind of a big departure from what we've been talking about. We have ground states and nice field series, and now I want to consider mixed states in an open quantum system. That means that the system is interacting with the environment. But we don't want to really know what happens in the environment. We just trace out the environment, integrate out environment. But then we are left with a mixed state. Right? It's not a pure state anymore. So in such an open system, quantum states are described by density matrices. Okay? And this is not something new. We use it all the time in STEMAC. Every thermal state at finite temperature is a mixed state. Right? It's a consequence of your system coupling to a Bass. But we ignore the Bass, so the system is in the Gibbs state. Okay. And a somewhat less familiar example is that you have some quantum states, and again, it's coupled to environment, but maybe not coupled to a thermal Bass. So you can also have non-thermal mixed states coming from quantum states with some decoherence. Okay. So let me just quickly flesh out the definition. A mixed state, a general quantum state, is a Hermitian positive semi-definite operator rho with unit trace. Okay, and if it's a rank 1 operator, means that it's just a projector, then it's a pure state. And in general, a mixed state is basically an ensemble of pure states. Okay, but this decomposition is not unique. So we should really think of rho as an operator, not as attached to a certain ensemble of pure states. Okay. All right. So we can kind of make analogy between pure states and mixed states. The states can be pure or mixed. In the case of pure states, we know the evolution of states are given by unitary operators. Okay. And the generalization of that to mixed states are quantum channels. Okay. So quantum channels map mixed states to mixed states and preserve all the properties, semi-positive definite and trace, unit trace. And we can think about a quantum channel in the following way. Okay? Again, from kind of coupling to environment. We have some states, rho. So here I show the states with, as pictorially this way, the legs means the Brian and cats. Okay. And you can add ancillars. These are the black dots. You can add some ancillars. And these ancilla interact with your system in some way. This is governed by some Hamiltonian that couples the system with the ancillars for some time. And then we trace out the ancilla, remove the ancilla, you get another mixed states. Okay. And because here we're doing many-body physics, I'd like to add locality condition to everything. So the ancilla is a bunch of qubits extensively, and Hamiltonian is local. The interaction between the system and the ancillas must be local, and that means you kind of entangle the system with the environment by a quasi-local unitary, and then you trace out the ancilla. So call this a quasi-local quantum channel. Okay. This is really just a mathematical abstraction model of a finite time dissipative evolution in the open system.
Okay. Sir, before beginning, can I ask something?
Sure.
In this page, for example, we are, as far as I understand, we are just considering product states, right? Or just
the rho doesn't have
short-range entangled?
I said short-range correlated, not short-range entangled. And there's a big difference between them. So the rho, at this point, the rho is just some general density metrics of the many-body system. But the ancillas, they start with as a product state. Indeed, that I didn't mention that. So here, I'm not sure whether people can see my mouse, but there's a product state for the ancilla. So ancilla begins with a product state. Right. So when I say ancilla, from now on, they are always at least they start from a product state.
Okay, thank you.
Yeah. So they're trivial product states, so you can add ancillas anytime you like. And this also was kind of implicit in the classification of gap Hamiltonian lattice that we allowed to stack trivial states. Otherwise, you compare states in one Hilbert space with another, which have different dimensions. There's no way to make them equivalent, but you can make up that by adding ancilla. Okay, so I've talked about density metrics and quantum channels. So I also need to, it turns out that you also need to generalize the notion of symmetry. And this might be the most important thing that that people have realized when you try to understand this kind of topological physics in mixed states, that we need to actually distinguish two different kinds of symmetries. So the obvious way to generalize symmetry is that symmetry commutes with the density metrics. That's how symmetry acts on operator. So if you have W that commutes with rho, and let's say W is a unitary operator, then this is a good symmetry, right? This is what I call a weak symmetry. So as one example, you can diagonalize the density matrix. For example, you can diagonalize the density matrix, and W just puts a face in front of each of the pure state in the decomposition. And the face could be different. If you have W from both sides, then the face cancels. Okay. So this is called weak symmetry. And there's a familiar example of weak symmetry. That is what we learned in undergraduate STEMAC, the grand canonical ensemble, right? And the symmetry there is the number conservation of particles, right? So the difference between canonical and grand canonical is that you have number conservation, and in the case of grand canonical, the coupling between system bass actually exchanges particle between system bass, even though the total number of particles is conserved. Now, there's a version that really generalizes the canonical ensemble, meaning that you couple it to a bass, but we don't allow the particle numbers of system to change. Right? It's only exchange energy between the system and bass. So mathematically, that means you multiply the density matrix by W just from one side, not from two, not from both sides, which might seem a little bit unnatural, because we are used to think of operators acting on symmetry acting on operators by conjugation, but here we need to act on one side. Doesn't really matter which side, because the rho is Hermitian. You can just take Hermitian conjugate to get action on the other side. So we'll just act from the left. And if you get the same density matrix up to a phase factor, we say the symmetry is a strong symmetry. Okay? The physics is the physics of a canonical ensemble, where you fix the number of particles. So U1 symmetry acting on the density matrix gives you a phase factor, just basically measures how many particles you have. And that's fixed. Unlike in grand canonical ensemble, the particle numbers can fluctuate. Okay, so even though these names might be a little unfamiliar, but the notions are deeply rooted in STEMAC, right? We've seen them. And there's a reason to call the strong symmetry strong, because you have W only on one side and you don't have W dagger on the other side. So that means all the phase information is kept for strong symmetry. For weak symmetry, you kind of lose any information that you have about phase vectors. The projective phase vectors are gone because you have W's from both sides. So that means anomalies, at least intuitively, anomalies are meaningful for strong symmetry, because anomalies are just some projective phase vectors in the end of the day. So that's one thing. And the second is that if you have a convex sum of density metrics, okay, that just means that you have some probabilistic ensemble of states that again gives you density metrics. And if this convex sum has a strong symmetry, one of them has to have that same strong symmetry with the same eigenvalue. So it's very strong. It constrains the convex decomposition of a density matrix. Okay. And the last one is perhaps the most important one. The strong symmetry can be commuted, or you can kind of say that you can pull it back through a quantum channel. Therefore, you can use it as invariant to characterize quantum phases. Okay. So let me say the last property more precisely. So suppose you have two density matrices, ρ1 and ρ2. And ρ1 is obtained from ρ2 by applying some quantum channel that I call n. Okay. And let's say that W is a strong symmetry of ρ1, so W ρ1 is equal to ρ1. It's a unitary operator. Okay. So I'll assume that W is always a unitary operator. And let's say it's an internal, it's like an internal symmetry, not like lattice translation or spatial rotation. Okay. And through some simple algebra, you can show that by just purifying W2, you'll find that W2 times some ancilla in the product state has a strong symmetry, which is W conjugated by U. And U here is a quasi-local unitary, because the N operator is N quantum channel is, we assume it's a quasi-local quantum channel. So that means you can kind of pull back a strong symmetry from ρ1 to ρ2 once you conjugate the strong symmetry with some unitary. And the unitary is quasi-local, so it preserves all the anomalies and all of these things of the strong symmetry. Okay. So there's a particular direction. If if ρ1 is obtained from ρ2, then you can take the symmetry of ρ1 to ρ2. Okay. You can kind of push it through the quantum channel in that direction, in this particular direction. Okay. So these are a few useful properties that I'll build on to discuss the topological order. So I guess my time is running short. So, but hopefully I can at least get a couple of examples through. Okay.
So
Now,
actually, if you have time, you can just go on.
okay.
There is
All right.
no time limit
Yeah.
if you are.
All right. Yeah. So,
Can I ask a quick question?
sure. Yeah, please.
At this stage, are we assuming anything about whether the symmetry is higher form and invertible? Anything? Like,
So
can we
far,
have?
actually, so far I haven't assumed anything about whether it's higher form or not, right? This W could be zero form, could be higher form. Yeah.
Okay.
And everything I've said so far applies to all of them.
Okay.
Because it's really just a statement in quantum mechanics. Right? I haven't really used anything about locality or how these operators are supported. This is really just a quantum mechanical statement. And the place where I need locality is later when we discuss, for example, when we actually have W as a higher form symmetry. And then then we have quasi-local channel, which means this U here is a quasi-local circuit. And then we can argue that this U dagger WU has the same sort of anomaly, the one that the begin with. Okay. Okay. All right. So so far this is really just quantum mechanics. There's nothing about mighty body. All these are things that you can just say for a quantum mechanical system. So now I want to really start talking about mixed state, but in the many body system. That means you want to really take locality seriously. So no, we can talk about a very general mixed state, but the space of mixed state is poorly understood. The general landscape of mixed state is still pretty poorly understood. So we like to do something that's a little more familiar. Okay, we like to limit ourselves within something that we can at least get a handle on. So I'll only talk about the mixed states that you can get by applying quasi-local quantum channels to ground states of local Hamiltonian. Okay. So that means you prepare some ground states and then you let this ground state, they let this system interact with the environment for some time and then you turn it off. And we look at the mixed state. Okay. I'm not saying that every mixed state can be prepared this way, but no, this is a kind of more easier to grasp set of states. Okay, and it captures lots of the examples that we are interested in. Even that is not quite enough. You need to again supply some conditions. For example, the second one is actually kind of automatic. If you assume the ground state we begin with has short range correlation, and then this rho also has short range correlation. Okay, so this, for example, rules out any spontaneous symmetry breaking of the zero form symmetry. Okay. But there are other conditions that one need to supply. And here, I'm not going to get into the details. I'll just say that at least we would like to also demand short range correlation in some more sophisticated sense, where certain nonlinear expectation value of local correlations should be short range. Okay, so this itself is a big topic that I can give a whole talk on. So I'll just say that we also need some additional conditions on these states. Okay. But with that in mind, so this is a little bit heuristic, but let me move on. So this again gives you a huge space of states. Even that space is huge, right? And we want to give some structure. So here there are different choices of what you mean by one state is equivalent to another. It kind of depends on what properties you really care about, okay? Because this is kind of operation that preserves certain properties. Which properties you want to preserve kind of determines what equivalence relations you want to impose. So at least here there are two versions of the story, and I'll focus on one version and I'll comment on the other one. Okay. So the equivalent relation as introduced in these recent papers is that if you can go from one state to another by a quasi-local quantum channel, as I defined a few slides ago, and you can go back maybe with a different quasi-local quantum channel. They don't have to be the same quantum channels. Then we'll say these two states are equivalent. Okay, and the reason to explicitly say that you need to be able to go back is because quantum channels, unlike unitaries, they are not invertible in general. Right? This is just thermodynamics, second law of thermodynamics. The time arrow is not invertible. You can go in one direction. You cannot just invert the evolution, unlike unitary evolution. But we can ask that there exists another quantum channel that takes you back to the initial state. If that's possible, then we'll say these two states are equivalent. So I'll refer to this definition as a two-way connectivity by quasi-local quantum channels. And this definition is clearly motivated by quantum error correction, where one channel kind of introduces a noise, and the other channel recovers the original state from the noisy state. So this is one direction is like polluting the state with noise, the other one is cleaning up the noise. And these are different quantum channels, generally different quantum channels. All right, so under this definition, again, the space is divided into different regions, and we can refer to these regions as topological order in mixed states. Okay. So here, I would like to, again, let me just emphasize that it's really important to have two-way connectivity, okay? Because you can easily write down a quantum channel that just takes whatever states you begin with to any other, well, not to any other state, but to a trivial product state by a local quantum channel. In fact, it's very easy to describe the channel. You have a state in the system, and you have some ancillar in the product state. Now I can apply a swap operator between the system environment. Just swap them. This is a unitary, finite depth unitary. This is depth 1 unitary. Okay, and then we throw away the environment. Now the original state is swapped into the environment, and you can throw it away. And now in the system you have a product state. Okay? So every mixed state can be turned into a product state by this kind of swap channel. So this one direction is always there, right? You can easily destroy a state. The more difficult thing is to build an interesting state. Okay. And the last point is that invertible states, I'm not going to say what it means, no. Just for those who know, that invertible states are two-way connected to trivial product states. As long as we don't impose any symmetries, then they are not interesting. Okay. All right. So I've already said that this two-way connectivity captures the recoverability noted by error correction, and there's a similar definition that's phrased in terms of fast or rapid local Lindeblad evolution. Okay. Now there's an alternate definition where you impose more conditions, more strict conditions on this quantum channels. So I'll discuss that later. I'll briefly discuss that later. Okay. All right. So it's again, I have talked about quantum channels, mixed states, spaces quite abstractly. So now let's actually look at example again using the Tori code. Okay. So this is the same slide I showed earlier. Just want to remind you that we have this standard Tori code model where the ground state is a bunch of a superposition of these closed loops in the X spaces. Okay, and now I want to apply some quantum channel to this state. Quantum channel describes some kind of local decoherence process. So before I go there, let me first give a quick argument that the Tori code state itself belongs to a non-trivial mixed state topological order. Okay? So you could imagine that because quantum channels are more powerful, I mean, not more powerful, but more general than unitaries. So maybe certain states, could be that a certain states which was considered non-trivial became trivial once we allow the more general definition. And that's indeed the case for invertible states. Invertible states, they were non-trivial in the kind of pure state definition, but now they become trivial. Okay. Now I want to argue that Tori code still belongs to a non-trivial mixed state phase. So the Tori code is the one that I showed on the previous slide, has this exact Z2 cross Z2 one-form symmetry with anomaly. Okay. So now the non-trivial step is to show that you cannot prepare the Tori code state from a product state with a quasi-local quantum channel. The other direction is trivial, right? So to show two-way connectivity, you just need to show that absence of two-way connectivity, you just need to show that you cannot start from a product state and prepare Tauric code out of this using quasi-local quantum channel. Okay, so to show this, we basically use this kind of symmetry, strong symmetry, kind of pulling back property that you can push a strong symmetry through a quantum channel. So if this was a case, and the Tauric code state has some one-form symmetry operator, so that means this product state also has the one-form symmetry operator. Okay, basically the same one-form symmetry operator. But this is a contradiction, because if you do this for all the one-form symmetry, and we know they have anomaly, the short-range product state cannot have anomalous one-form symmetry. Okay? This is not possible. Basically, this is forbidden by the anomaly. So we get a contradiction. So that means you cannot prepare a Tauric code starting from a product state. So Tauric code still belongs to non-trivial mixed state topological order, even though with this more kind of coarse, more general definition of equivalence. All right. Just note the kind of a take-home message is that quasi-local quantum channels cannot produce anomalous strong symmetries from product state. Basically, cannot change anomalous strong symmetries. I mean, we have to make this statement more carefully, but no, that's roughly the idea. Okay, but let's see what the coherence can do to a Tauric code. So I guess I'm already running out of the 1 hour frame, but I'm gonna continue and hopefully get to the end of the story. Okay, so let's see what happens if you actually have decoherence, turn on some sort of decoherence on Tauric code. And this model of decoherence was studied in this classical paper by Dennis, Kitaev, Landau, and Priscil as a model for topological memory. And that was 24 years ago. And recently, this example was kind of examined from a many-body phase equivalence perspective in the recent paper, in the recent work. So what's a quantum channel? Well, instead of looking at equations, let me just say it in words. So what happens that you're allowed to apply X operator to each edge. Okay, so there's an independent process on each edge where you just apply X. But that happens with probability, right? That happens with probability P. So with probability P, you apply the X operator to an edge, and with probability 1 minus P, you don't do anything. Okay? And this happens across all the edge independently with the same probability. Okay, and I'll call this a bit flip channel. So this P is a probability, and it's easy to see that really the maximum value of P is 1/2. Right? You can have equal probability of applying X or not, and that's a maximum sort of random case that you can imagine. Okay, so if you do this to a Tauric code, pure state, you get some mixed state. You need some fluid. Okay, and I'll call this, and you get a phase diagram as a function of the parameter P. So P equals 0 is just Tauric code. P equals 1/2 is where you apply X with equal probability across all the edges. And in between, there's something happens. Okay. And you can imagine that if P is small, the probability of turning on this operator X is small, then the mixed state is very close to the pure state and nothing too much happens. And the state remains non-trivial until some critical value of P, where a phase transition happens, a phase transition mixed state happens, and it goes to a different phase, which is called a decohered Tauric code. Okay. So we can look at this phase diagram from the point of view of higher form symmetry. So just like introducing this term in Hamiltonian, this one explicitly breaking the strong one-form symmetry generated by, well, hopefully I have the same notation by E. Okay, one of the strong one-form symmetry. Actually, it's exactly the same notation. So there's a Z operators. It breaks the Z operator, right? It preserves the X. So there's one-form symmetry generated by X. And one can show that within this window of 0 to PC, you can still recover the same Z2 cross Z2 one-form symmetry. So it's still anomalous, and it's still in the same Topological phase. However, beyond that, you just have one of Z2 one-form symmetry. And this one is not anomalous. You lose the other one forever. Okay, so we can also look at what happens to the state, right? And this is easy to do in the limit where P equals 1/2, deep in the decohered Topological phase. So you can actually write down the wave function, the density matrix in the eigenstate basis of Hamiltonian. And that means you can work out algebra, you'll just see that it's a convex sum of all the excited states with some M configuration, with some M violations, but no E. Okay. So the pictorial is just, you have the sum of a mixture of all possible states with some M's. Okay, okay, so that's a state. But density matrix is an operator, so you can write it in different bases, right? So if you write it in the excitation basis, it looks like, Topological states with all possible M anyons. But we can also write it just in the X basis. And it turns out that if you write in the X basis, it looks somewhat differently. And it actually becomes simple. So in the X basis, it becomes a mixture of all possible loop configurations. So you should compare this with the ground state wave function, where you have a superposition of all the loop configurations. And here we have an ensemble of all the loop configurations. Okay, we can think of it as a classical Z2 gauge theory, where these blue lines are Z2 gauge fields. And this is a trivial state because each of them is a product state. And we have a mixture of product state. So this is a trivial state from my definition. Okay. And I'll just say that without going into details, if you start from a product state, you can prepare this state by a finite depth quantum channel. Okay, so in short, a quasi-local quantum channel can classically gauge a zero-form symmetry to prepare this kind of state of a classical Z2 gauge theory. All right. So this is a good example to demonstrate the effect of a quantum channel. So in one basis, it looks like you just incoherently proliferating some anyons. In this case, it's an E. It's an M anyon, right? You proliferate M anyons throughout the whole system, you get a mixed state. In the other basis, it looks like you are classically gauging a Z2 symmetry, and you get ensemble of loop states. Okay, so this is what happens in Topological code, but we can now explore what other options there are. And in the Topological code, there's a fermion excitation, so you can try to proliferate the fermions. So you can design a quantum channel, maybe not the one that actually happens in a real system, but at least theoretically you can do that. And you also get a phase diagram, but now the operators the operators create these fermions out of vacuum with some probability. If you do it correctly, and you get a following phase diagram, basically same phase diagram, but the other side of the transition remains non-trivial. And this is because on the other side, you have anomalous one-form symmetry. Okay? Anomalous, at least for spin system, it has a 't Hooft anomaly. Because it's a line that generates fermions, generated by the fermionic anyon. So it has anomaly. So even though the phase diagram looks similar, but now we have a non-trivial phase transition from non-trivial phase to another non-trivial phase. Okay? Even though they are different, but they are both non-trivial. So these two phases can be characterized by emergent Z2 cross Z2 one-form symmetry on one side, and on the other side you have a Z2 one-form anomalous Z2 one-form symmetry. Both are anomalous. Okay? And now, if you look at it from the kind of a category point of view, this Z2 anomalous one-form symmetry is the one that I discussed as example of premodular category. Okay? Well, it just has a fermion. So this is something not possible in ground state, at least in bosonic systems. Because the ground state, the one-form symmetry, the emergent one-form symmetry has to give you a modular tensor category. And here it's a premodular category. So this is beyond what you can do in the ground state, even though you start from ground state and just kind of mess it up. But you end up with a state that's still non-trivial. So we can call it an intrinsically mixed state that you cannot get this similar things in ground state. Okay. All right. So this example kind of demonstrates a few useful facts about mixed states, about quantum channels. And let me just summarize these things in kind of a few statements. So first, you can ask what quantum channels can do to these one-form symmetries, to strong one-form symmetry, because it seems like the strong one-form symmetries are useful to characterize these phases because they remain kind of robust under quantum channels. Well, so they can proliferate some anyons, and as a result, it shrinks the one-form symmetry to a smaller subset. Okay. But on the other side, and you can also kind of increase the one-form symmetry by classically gauging some zero-form symmetry. So it changes one-form symmetry in kind of two ways, basically. One is to shrink it to go to a subcategory using the language of category theory. The other one is to kind of increase it, but in a particular way. Okay. And by doing these, you can create categories that are not possible to find in ground state topological order. So these are the take-home messages. So we have other examples discussed in many details in the paper. So if you're interested, you can take a look at them. So now let me just, using the last few minutes, I'll just say what our conjecture of the classification is. So this is conjecture. Okay. The conjecture is basically what I just said. So the ground state topological order are classified by modular tensor categories. Okay. These are essentially describing the generalized one-form symmetries in the ground state. Now, conjecturally, each topological mixed state is associated with a strong one-form symmetry described by a premodular category. Okay. So you just drop the modularity condition and that's it. Okay. Okay. So you can at least associate to each topological mixed state with such a category. And we conjecture that under some conditions, under some further equivalence on this premodular category, that classifies the mixed state under this kind of two-way connectivity condition. Now you can ask whether these premodular categories, when two premodular categories describe the same state. So as an example, you can have a trivial state with the so-called Rab-G symmetry. Rab-G is a kind of trivial premodular category in this sense. Okay, this is a category of representations of finite dimensional representations of some group G. So again, turning some of the statements into mathematical equations, there are two effects of quantum channel. One of them is to incoherently proliferate anyons. So that means you start from C, which is the original state, you go to a subcategory, which I call C tilde. Okay. You start from mixed state with premodular category C, you can go to a subcategory. So that's one thing. And you can also, so that's what I mean when I say you can shrink the one-form symmetry going to a subcategory. But you can also enlarge it by classically gauging a zero form symmetry. So that means you go from C to C tilde, but the relation between them is that if you start from C tilde and you condense or you quotient out by transparent lines, you get C. Okay. So these are the two effects. Physically, these are two effects that quantum channels can have on the premodular category for topological mixed state. Okay. And there's a useful kind of mathematical description of the relation that is these two implies you can apply these two operations to the categories, multiple times. Okay. But these two imply that there's a braided tensor functor going from C tilde to C. Okay, so C tilde is obtained from C by quantum channel, but now there's a braided tensor functor that goes from C tilde to C. Okay. This is slightly weaker than the actual two things that quantum channel can do, but it's a useful kind of mathematical thing that we can discuss. So now we can just ask, suppose you have two-way connectivity. So that means the two categories, you have braided tensor functors in both directions. Now this is a mathematical problem. What does that imply? It turns out that implies C1 and C2, they have to take this form. There is another premodular category B, which is common in both equations. And C1 has to be B times S1. C2 has to be B times S2. Here, the box product is a Deligne product, just kind of stacking two series together. So B is some common premodular category. S1 and S2 are so-called symmetric categories. Sometimes they are called Tannakian or super Tannakian. Basically, they are fully transparent lines. So this is just some mathematical fact that one can show, starting from the assumption that there are braided tensor functors in both directions. And then there's a further physical argument to show that both S1 and S2, they both have to be basically Tannakian categories. That is, they are representation categories of some finite groups. Can be different groups, but they have to be representation categories of some group. Okay, so that means you can freely Deligne product some rep G to the premodular category, but that's it, right? So up to this kind of stacking of trivial rep G categories, C1, C2, if they are connected by two-way equivalence connectivity, then they must be the same premodular category. So in this sense, our conjecture is that premodular category classifies the topological mixed states. Okay, so last few comments. So again, unlike the ground state case, now it really depends on what definition you take, and you get different results. So the two-way connectivity is a useful definition because it captures kind of a recoverability property in the error correction. But you might say that it's still too coarse. Okay? For example, the fully decohered code is considered trivial because you can prepare this by a quasi-local quantum channel from product state. So it's trivial under this definition. However, if you look at it, it is actually a classical topological memory. It's classical, but it's topological memory. Okay. So you might want to consider this also as a non-trivial state. It has some non-trivial structure in it. There's no quantum entanglement, but it has some non-trivial classical topological memory. So you might want to have a definition where this is actually non-trivial. So such a definition was proposed in a more recent paper, this paper by Shenqi Sang and his collaborators, where you, very roughly speaking, that you replace quasi-local quantum channel with local reversible ones. And now the decohered code actually belongs to a non-trivial phase. Okay, so I'll just say that under this alternative definition, more refined definition, you not only need to know the anomalous strong one-form symmetries, you also need to know something about the weak symmetries. I haven't talked about weak symmetries, weak one-form symmetry, then especially the weak mixed anomaly between them. Okay, so that's also some kind of invariant. But no, I'll stop here about, that's all I want to say about the phase equivalent. Just the fact that you actually now have different options These options capture different physics. The two-way connectivity seems to be the most coarse, that only knows about a strong one-form symmetry, and you can make a more fine-depth classification that captures some other properties. All right, I'll skip this and I'll just end on this slide that there you can go and study topological mixed states, and we have a conjecture of the classification, and I think this is still a lot of things we don't understand about these mixed states, higher dimensions, or a more kind of rigorous approach to this, and this is still a very much ongoing subject. Okay, I'll stop here, and thank you all for attention. I'm taking too much time.
So thank you for the great talk. If there are questions, we can just take a couple.
Yeah, sure.
Can I ask one question? First of all, thanks for the nice talk. You kept mentioning some notion of classical gauging. I didn't exactly get what it is. Can you give like maybe a continuum intuition for it?
Yeah, so yeah, let me say in words. I think that's probably like continuum intuition. So let's first say what we mean by gauging in usual. Okay, so let's say what we mean by gauging. In the quantum field theory, what you mean by gauging that you start from some field theory, let's say in Euclidean space-time, and you couple it to a background gauge field, right? You can always couple, if you have symmetry, you can couple it to background gauge fields. And then in the path integral, you integrate over all the background gauge fields, right? To sum over all of them, that's standard gauging. You can also think about it in terms of like the Poincaré dual picture. You insert some defects, you sum over all possible defects. Okay. So this is in path integral, in Euclidean path integral. At the level of states, what happens is that you can also couple to, starting from some wave function, for example, you can couple to background gauge fields. You get a new wave function. And then you superpose all such states with all possible configuration of background gauge fields.
Okay.
So the way, if you can do it consistently, I mean that the symmetry is non-anomalous and you get a gauged state, or you get a gauged theory. So now what I mean by classical gauging, this is something that we invented. Well, we just invented this word. I'm not sure it's standard. Is that now we only do it at level of states. You start from state with some symmetry. Okay. The density matrix has some symmetry, and you can couple it to background gauge fields as well. You can insert defects to the density matrix and get a new state. But now, instead of summing, because these are density matrices, you cannot just superpose them, but you can form a mixture of them. You can form a convex sum of these density matrices coupled to background gauge fields, and you get a new state. Right? This is what I call classical gauging.
I see. Okay.
So you can imagine doing this in continuum, right? Even though I'm not sure how to actually write down a continuum theory for this, but I don't think there's any obstruction in defining this in continuum. This is just like kind of like well, I call it classical gauging because you go from a mixed state to another mixed state.
I see.
And because they're all mixed states, you don't really have any phase information. This is just a probabilistic mixed state.
Now it's more clear. Thank you. Thanks for the help.
So we can take one more question. If there are no, we can just stop recording. Let's wait for someone. So, okay, I'm